Hello students, in this lecture we will discuss about the thermodynamic relations. Now we will discuss certain mathematical relations which are quite useful in establishing thermodynamic relations. There are three theorems, the results of which are quite important while establishing thermodynamic relations. The derivation of these theorems is not so important, but their results are quite important as far as thermodynamics is concerned. Now theorem first, if a relation exists among the variables x, y and z, then z may be expressed as a function of x and y, or you can say dz is equal to del z upon del x when y is constant into dx plus del z upon del y when x is constant into dy. If del z upon del x when y is constant is equal to m and del z upon del y when x is constant is equal to n, then we can write this expression as dz is equal to m dx plus n dy. Now we differentiate m with respect to y when x is constant and n with respect to x when y is constant. So we get that del m upon del y when x is constant is equal to del n upon del x when y is constant. That is equation 3.67. This is the condition of exact or perfect differential. If a quantity f is a function of x, y and z and relation exists among x, y and z, then f is a function of any two of x, y and z. Similarly, any one of x, y and z may be regarded to be a function of f and any one of x, y and z. Thus, if x is such that x is function of f and y, then dx is equal to del x upon del f when y is constant into df plus del x upon del y when f is constant into dy. Similarly, if y is such that y is function of f and z, then dy is equal to del y upon del f when z is constant into df plus del y upon del z when f is constant into dz. Substituting the expression of dy in the preceding equation, dx is equal to del x upon del f when y is constant into df plus del x upon del y when f is constant into del y upon del f when z is constant into df plus del y upon del z when f is constant into dz. This is equal to del x upon del f when y is constant into df plus del x upon del y when f is constant into del y upon del f when z is constant into df plus del x upon del y when f is constant into del y upon del z when f is constant into dz. Again, we can say that dx is equal to del x upon del f when z is constant into df plus del x upon del z when f is constant into dz. Del x upon del z when f is constant is equal to del x upon del y when f is constant into del y upon del z when f is constant. This gives us a result that del x upon del y into del y upon del z into del z upon del x for all the terms when f is constant is equal to 1. This is equation number 3.68. Theorem third. Among the variables x, y and z, any one of the variables may be considered as the function of other two. X is such that x is considered as the function of y and z. Dx is equal to del x upon del y when z is constant into dy plus del x upon del z when y is constant into dz. Similarly, del z is equal to del z upon del x when y is constant into dx plus del z upon del y when x is constant into dy. So dx is equal to del x upon del y when z is constant into dy plus del x upon del z when y is constant into del z upon del x when y is constant into dx plus del z upon del y when x is constant into dy. Now this is equal to del x upon del y when z is constant plus del x upon del z when y is constant into del z upon del y when x is constant into dy plus del x upon del z when y is constant into del z upon del x when y is constant into dx, which is equal to del x upon del y when z is constant plus del x upon del z when y is constant into del z upon del y when x is constant into dy plus dx. Now this gives del x upon del y when z is constant plus del x upon del z when y is constant into del z upon del y when x is constant is equal to 0. So this gives the result del x upon del y when z is constant into del z upon del x when y is constant into del y upon del z when x is constant is equal to -1. Among the thermodynamic variables P, V and T, the following relation holds good. Del P upon del V when T is constant into del V upon del T when P is constant into del T upon del P when V is constant is equal to -1. So now we will be discussing property relations and then Maxwell's equations. As you know that property is the physical quantity, the value of which basically depends upon the end states, not on path. And the property, which is also known as point function, is basically expressed with exact differential. For example, in the equation first, second, third, fourth, U, that is internal energy, T temperature, S entropy, P pressure, V volume, H enthalpy, F Helmholtz function, G Gibbs function, they all are basically property, or you can say point function. Now a pure substance existing in the single phase has only two independent variables, and out of 8 quantities, that is P, V, T, S, U, H, F, that is pressure, volume, temperature, entropy, internal energy, Helmholtz function, enthalpy and Gibbs function, any one may be expressed as a function of any other two others. For a pure substance undergoing an infinitesimally reversible process, du is equal to TdS minus PdV. If you look at this first equation, this is basically derived from the first law of thermodynamics, that is expressed for the flow system. You must have studied del Q is equal to du plus del W. So du is equal to del Q minus del W. So you know that for the reversible process, del Q has been written as TdS, and for the reversible process, del W, that is work, non-flow work, that has been written as PdV. So from there we have got this first property relation, that is d is equal to TdS minus PdV. Now enthalpy is equal to U plus PV, H is equal to U plus PV. So differentiating it, we get du plus PdV plus VdP. Now in place of du we have written TdS minus PdV. So finally minus PdV gets cancelled with the plus PdV, and finally we get dH is equal to TdS plus VdP. Now Helmholtz function f is equal to u minus Ts. So differentiating we get dF is equal to du minus TdS minus S dt. Now putting the value of du over here, we get finally minus PdV minus S dt. Now Gibbs function is equal to H minus Ts. So differentiating we get dg is equal to dH minus TdS minus S dt. Now putting the value of dH here, finally we get VdP minus S dt. Since U, H, F and G are thermodynamic properties and exact differentials of the type, dz is equal to mdx plus ndy, means any one of the property relation above is written in the form of dz is equal to mdx plus ndy. So the first theorem is applicable over here, that is del m upon del y when x is constant is equal to del n upon del x when y is constant. So applying this to 4 equations, we get these 4 relations which are known as Maxwell relations. Del t upon del v when s is constant is equal to minus del p upon del s when v is constant. Del t upon del p when s is constant is equal to del v upon del s when p is constant. Del p upon del t when v is constant is equal to del s upon del v when t is constant. Del v upon del t when p is constant is equal to minus del s upon del p when t is constant. Now we will discuss TDS equations. Basically, there are 3 TDS equations. In the first TDS equation, entropy is assumed to be function of temperature and volume. And for the second TDS equation, entropy is assumed to be the function of temperature and pressure. In the third TDS equation, which is not discussed in this lecture and which is not that much important from thermodynamic relations point of view, entropy is assumed to be the function of pressure and volume. So, first of all, we will discuss first TDS equation. Here entropy is function of temperature and volume. So ds is equal to del s upon del t when v is constant into dt plus del s upon del v when t is constant into dv. Now multiplying both sides by absolute temperature, we get TDS is equal to T into del S upon del T when V is constant into dt plus T into del S upon del V when T is constant into dV. Since T into del S upon del T when V is constant is equal to Cv, that is heat capacity at constant volume. So we substitute Cv in the first term of right hand side, and moreover by using third Maxwell relation, we also substitute del P upon del T when V is constant is equal to del S upon del V when T is constant. With this expression, we substitute the second term on the right hand side of the equation. So finally we get TDS is equal to Cv dt plus T into del P upon del T when V is constant into dV. This is first TDS equation. Now to obtain the second TDS equation, we assume as entropy to be function of temperature and pressure. So ds is equal to del S upon del T when pressure is constant into dt plus del S upon del P when temperature is constant into dP. Since T into del S upon del T when pressure is constant is equal to Cp, that is heat capacity at constant pressure. So del V upon del T when pressure is constant is equal to minus del S upon del P when temperature is constant. This is basically the Maxwell's fourth relation. So now we will substitute the first term with the Cp and the second term with the Maxwell's fourth relation. So finally we get TDS is equal to Cp dt minus T into del V upon del T when pressure is constant into dP. This is basically the second TDS equation. Now we will obtain the expression for difference in heat capacities. Now equating the first and second TDS equation, we get TDS is equal to Cp dt minus T into del V upon del T when P is constant into dP, which is equal to Cv dt plus T into del P upon del T when V is constant into dV. Now rearranging the terms, we have Cp minus Cv into dt is equal to T into del P upon del T when V is constant into dV plus T into del V upon del T when P is constant into dP. Now we take the Cp minus Cv term on the right side of the equation and we obtain this expression, that is dt is equal to T into del P upon del T when V is constant into dV upon Cp minus Cv plus T into del V upon del T when P is constant into dP upon Cp minus Cv. Now assuming temperature to be function of volume and pressure, we have this expression dt is equal to del T upon del V when P is constant into dV plus del T upon del P when V is constant into dP. Now we compare the expression third and fourth on the slide with each other. So we equate the coefficients of dV as well as we equate the coefficients of dP for both of these expressions, that is expression third and expression fourth on the slide, and we get T into del P upon del T when V is constant upon Cp minus Cv is equal to del T upon del V when P is constant, and T into del V upon del T when P is constant upon Cp minus Cv is equal to del T upon del P when volume is constant. Now from both these equations that we obtained in the last of the previous slide, we get Cp minus Cv is equal to T into del P upon del T when V is constant into del V upon del T when P is constant. Now as we have obtained this expression from the theorem third, we can say del P upon del V when T is constant into del V upon del T when P is constant into del T upon del P when V is constant is equal to -1. Now substituting this expression in place of del P upon del T when V is constant in the first expression of this slide, we will get Cp minus Cv is equal to minus T into del V upon del T square when P is constant into del P upon del V when T is constant. Now we will derive some important conclusions from the equation that we have derived just now, that is Cp minus Cv is equal to minus T into del V upon del T square when P is constant into del P upon del V when temperature is constant. Since del V upon del T square when P is constant is always positive because it is the square of a quantity, so it will always be a positive. And del P upon del V when temperature is constant for any substance is always negative because it is basically a slope of isothermal process, so it will always be negative because when the compression is taking place, then pressure is increasing but volume decreases, and when expansion is taking place, then pressure is decreasing and volume is increasing. So del P upon del V when temperature is constant will always be negative. So finally Cp minus Cv will always be a positive because on the right hand side we will always have a positive thing. So Cp minus Cv is always a positive, therefore Cp is always greater than Cv. Second, as the absolute temperature approaches 0 Kelvin, then Cp will approach Cv. Means Cp is equal to Cv is only possible at 0 Kelvin temperature. Third, when del V upon del T is equal to 0, when pressure is constant. For example, for water at 4 degrees Celsius, when density is maximum and specific volume is minimum, then del V upon del T with constant pressure will bear 0 value. So for that condition, Cp will always be equal to Cv. So Cp minus Cv is always a positive quantity, means Cp is always greater than Cv except these two conditions, that is either the temperature is equal to 0 Kelvin or at the condition of maximum density or minimum specific volume. Now for an ideal gas, PV is equal to MRT, where M is mass, R is gas constant, T is temperature, that is absolute temperature, P is pressure and V is volume. Now del V upon del T when pressure is constant is equal to MR upon P, which is equal to V upon T, and del P upon del V when temperature is constant is equal to MRT upon V square. By substituting these two values in the expression, we will get Cp minus Cv is equal to Mr. So for the unit mass, Cp minus Cv is equal to R, which is an important relation that we have been using since our school times. But now its derivation is in front of us. We have now derived, and we can say that Cp minus Cv is equal to R. That has been mathematically proved. Now this expression Cp minus Cv is equal to minus T into del V upon del T square when P is constant into del P upon del V when temperature is constant may also be expressed in terms of volume expansivity, which is defined as the fractional change in volume with change in temperature when pressure is constant. And one more term, that is isothermal compressibility, which is defined as the negative of the fractional change in volume with change in pressure when temperature is constant. Now Cp minus Cv is equal to T into V into beta square upon Kt. This is the final expression that we have obtained when we have substituted the expression of beta and Kt in the above equation, that is the equation written as the first expression on this slide. Ratio of heat capacities. Now from the first and second TdS equation, if we keep entropy as constant, we can get these two expressions. Cp into dt when entropy is constant is equal to T into del V upon del T when pressure is constant into dP when entropy is constant. Second expression is Cv into dt when entropy is constant is equal to minus T into del P upon del T when volume is constant into dV when entropy is constant. Now dividing the first expression by the second expression, we get Cp upon Cv is equal to minus del V upon del T when pressure is constant into del T upon del P when volume is constant into del P upon del V when entropy is constant, which is written as del P upon del V when entropy is constant upon del P upon del V when temperature is constant, by using the result of theorem third, and that has been written as gamma. Why? Because in the numerator we are having slope of isentropic process. Now if this isentropic process is reversible, it will also be adiabatic. Similarly in the denominator we are having the slope of a reversible isothermal process. So we can say that slope of reversible adiabatic process is gamma times the slope of a reversible isothermal process. Now since we know that the value of gamma is greater than 1, so we can say that slope of a reversible adiabatic process or isentropic process is greater than the slope of a reversible isothermal process. Now here on the PV diagram we are basically showing you the compression work for reversible adiabatic process and reversible isothermal process. As we have discussed that slope of isentrop is greater than that of isotherm on PV diagram. Now here the work during the compression for isentrop is shown by the area 12S341, whereas for the reversible isothermal compression the work done is represented by 12341. So you can compare the compression work for the two different processes, that is reversible isothermal process and reversible adiabatic process. So as we have seen that isothermal compression requires minimum work, and the polytropic process lying between the isothermal process and the adiabatic process, we can say that n is greater than 1 and less than gamma. So for the polytropic process, the work done will be between these two values, that is between that of a reversible isothermal process and that of reversible adiabatic process. So adiabatic compressibility, Ks, is defined as the fractional change in volume with the fractional change in pressure when entropy is constant. So now Cp upon Cv has been written so that we can obtain the ratio of Cp and Cv in terms of Kt and Ks, where Kt is the isothermal compressibility and Ks is the adiabatic compressibility. And finally we get the expression that is 3.77. Now we are going to prove an important concept, that is internal energy of an ideal gas is a function of temperature only. Now for a system that is undergoing an infinitesimally reversible process between two equilibrium states, the change of internal energy is d is equal to TdS minus PdV. Now the first TdS equation is TdS is equal to Cv dt plus T into del P upon del T when V is constant into dV. Now substituting the first TdS equation in the above equation, we get du is equal to Cv dt plus T into del P upon del T when V is constant into dV minus PdV. Now taking dV as common for the second and third term, we get the equation 3.78. Now if U is such that U is function of temperature and volume, then we can say du is equal to del U upon del T when V is constant into dt plus del U upon del V when T is constant into dV. Now comparing the two equations means this equation and the equation on the previous slide, we get del U upon del V when temperature is constant is equal to T into del P upon del T when V is constant minus P. Now for an ideal gas, P is equal to mR T upon V. Now del P upon del T when V is constant is equal to mR upon V, which is equal to P upon T. And del U upon del V when T is constant is equal to T into P upon T minus P. We have substituted the value of del P upon del T when V is constant, which was coming out to be P upon T, in the equation 3.79, and we get the value del U upon del V when temperature is constant equal to 0. It basically implies that U does not change even when V is changing if the temperature is constant. Now from the result of theorem 2, you can say that del U upon del P when temperature is constant into del P upon del V when temperature is constant into del V upon del U when temperature is constant is equal to 1. Now we take the third term on the right hand side and we get del U upon del P when temperature is constant into del P upon del V when temperature is constant is equal to del U upon del V when temperature is constant, which is equal to 0, as we have proved on the last slide, previous slide. So del P upon del V when temperature is constant can never be 0 because it is the slope of a isothermal process and it can never be 0. So we can say that if right hand side is 0 and we are having product of two quantities on the left hand side of the second expression, then one of the term has to be 0, and as we have said that del P upon del V when temperature is constant is not equal to 0, it implies that other term, that is del U upon del P when temperature is constant, has to be 0. And it says that U does not change either when P changes at isothermal process, constant temperature process. So earlier we proved that U does not change even when V is changing if the temperature is constant. Now we have proved that U will not change even when P is changing if the temperature is constant. So it means U will change only when temperature will change. So it means internal energy of an ideal gas is function of temperature only. Now PV is equal to MRT and T into del P upon del T when V is constant minus P is equal to 0, as we have proved on the previous slides. So we can say that du is equal to CVDT holds good only for an ideal gas in any process, even when the volume is changing. But for the other substances, du is equal to CVDT is true only when volume is constant. Now we want to prove that enthalpy of an ideal gas is function of temperature only. So as we have done for the internal energy, similarly we consider a system that is undergoing a infinitesimal reversible process between two equilibrium states, and for that the change of enthalpy is dH is equal to TdS plus VdP. Now the second TdS equation is TdS is equal to CpdT minus T into del V upon del T when pressure is constant into dP. So substituting this second TdS equation in the above equation, we get dH is equal to CpdT plus VdP minus T into del V upon del T when pressure is constant into dP. So we obtain dH is equal to CpdT plus V minus T into del V upon del T when pressure is constant into dP. Now if enthalpy is such that and it is function of temperature and pressure, we can say dH is equal to del H upon del T when pressure is constant into dt plus del H upon del P when temperature is constant into dP. So when we compare the equation on the previous slides with this equation, then we get dH upon del P when temperature is constant is equal to V minus T into del V upon del T when pressure is constant. Now for an ideal gas, V is equal to MR T upon P. So del V upon del T when pressure is constant is equal to MR upon P, which is equal to V upon T. So del H upon del P when temperature is constant is equal to V minus T into V upon T, which becomes 0. So it says that enthalpy does not change even when pressure changes at constant temperature. Now using the result of theorem second, we get del H upon del V when temperature is constant into del V upon del P when temperature is constant into del P upon del H when temperature is constant is equal to 1. Now we take the third term on the right hand side and we get del H upon del V when temperature is constant into del V upon del P when temperature is constant is equal to del H upon del P when temperature is constant. Now this right hand side term is equal to 0, as we have proved on the previous slide. So it means the product of two terms is there on left hand side and one of them has to be 0. Now since the second term, that is del V upon del P when temperature is constant, it is the reciprocal of the slope of isotherm, and if del P upon del V when temperature is constant is not equal to 0, so definitely its reciprocal will also be not equal to 0. So definitely the first term on the left hand side has to be 0, that is del H upon del V when temperature is constant has to be 0. It basically implies that enthalpy will not change either when volume changes at constant temperature. So enthalpy of an ideal gas is function of temperature only. Now as P into V is equal to MRT for an ideal gas and V minus T into del V upon del T when pressure is constant is equal to 0. So we can say dH is equal to Cp dt holds good only for an ideal gas in any process even when the pressure changes. But for any other substance other than the ideal gas, dH is equal to Cp dt is true only when pressure is constant. Joule-Kelvin effect. When a fluid passes through a restriction, such as a porous plug, a capillary tube, or an ordinary wall, its pressure decreases. As we have discussed this topic, that is throttling process, while discussing the steady flow processes, we discussed that enthalpy of the fluid remains approximately constant during a throttling process, and that the fluid experiences a large drop in its temperature as a result of throttling, which forms the basis of operation for refrigerators and air conditioners. But this is not always the case. That temperature has to decrease. The temperature of the fluid may remain unchanged, or it may even increase during a throttling process. So there are three possibilities: that along with pressure drop, temperature may increase, temperature may decrease, or temperature may remain constant. The temperature behavior of a fluid during a throttling while enthalpy is constant is described by Joule-Thomson coefficient, which is defined as change in temperature per unit change in pressure when enthalpy is constant. Thus, the Joule-Thomson coefficient is a measure of change in temperature with pressure during a constant enthalpy process. Now, pressure drop has to take place, this is for sure. But with pressure drop, if temperature is increasing, then Joule-Thomson coefficient will be negative. If with pressure drop, there is no change in temperature, temperature is remaining constant, then the value of Joule-Thomson coefficient will be equal to 0. But if the temperature decreases along with the pressure drop, then Joule-Thomson coefficient has to be positive. If we look carefully at defining equation, we come to know that Joule-Thomson coefficient represents the slope of constant enthalpy lines on TP diagram. Such diagrams can be easily constructed from temperature and pressure measurements alone during throttling processes. A fluid at fixed temperature and pressure T1 and P1, thus fixed enthalpy, is forced to flow through a porous plug, and its temperature and pressure downstream T2 and P2 are measured. The experiment is repeated for different sizes of porous plugs, each giving a different sets of T2 and P2. Plotting the temperatures against the pressures gives us constant enthalpy lines on a TP diagram as shown in the figure on slide. Now we repeat the experiment for different sets of inlet pressure and temperature, and we plot the results. And therefore, thereby we can construct a TP diagram for a substance with several constant enthalpy lines. Some constant enthalpy lines on TP diagram pass through a point of zero slope or zero Joule-Thomson coefficient. The line that passes through these points is called the inversion line, and the temperature at a point where constant enthalpy lines intersect the inversion line is called the inversion temperature. The temperature at the intersection of the P0 line, that is on the ordinate, that is y-axis, and the upper part of the inversion line is called the maximum inversion temperature. Now one can notice that the slopes of constant enthalpy lines are negative at states to the right of the inversion line and positive to the left of the inversion line. The throttling process proceeds along a constant enthalpy line in the direction of decreasing pressure, that is, from right to left. Therefore, the temperature of a fluid increases during a throttling process that takes place on the right hand side of the inversion line. However, the fluid temperature decreases during a throttling process that takes place on the left hand side of the inversion line. It is clear from this diagram that a cooling effect cannot be achieved by throttling unless the fluid is below its maximum inversion temperature. This presents a problem for substances whose maximum inversion temperature is well below the room temperature. For example, hydrogen is there. For hydrogen, the maximum inversion temperature is minus 68 degrees Celsius. Thus, hydrogen must be cooled before this temperature if any further cooling is to be achieved by throttling. Now, here we want to develop a general relation for the Joule-Thomson coefficient in terms of specific heats, pressure, specific volume and temperature. The difference in enthalpy between two neighboring equilibrium states is given by the relation dH is equal to TdS plus VdP. And the second TdS equation per unit mass is TdS is equal to Cp minus T into del V upon del T when pressure is constant into dP. Now dH is equal to Cp minus T into del V upon del T when pressure is constant minus V into dP. Now for constant enthalpy process, we will say dH is equal to 0. Hence, the Joule-Thomson coefficient, which is equal to del T upon del P when H is constant, will become equal to 1 upon Cp into T into del V upon del T when pressure is constant minus V. So this is basically the general relation for Joule-Thomson coefficient can be determined from the knowledge of pressure, specific volume and temperature and PVT behavior of the substance. Of course, it is also possible to predict the constant pressure specific heat of a substance by using Joule-Thomson coefficient, which is relatively easy to determine together with the PVT data for the substance. Now for the unit mass of an ideal gas, PV is equal to RT. So del V upon del T when P is constant is equal to R upon P, which is equal to V upon T. So Joule-Thomson coefficient, which is del T upon del P when H is constant, is equal to 1 upon Cp into T into V upon T minus V, which becomes 0 as the bracketed term is 0. Now we want to express the Joule-Thomson coefficient in terms of volume expansivity, that is beta. And we know that beta is 1 upon V into del V upon del T when pressure is constant. So the Joule-Thomson coefficient in terms of volume expansivity becomes V upon Cp into Bt minus 1. Now for an ideal gas, beta is equal to 1 upon T. So the Joule-Thomson coefficient becomes equal to 0. Clausius-Clapeyron equation. As we have come to know that Maxwell relations are significant in thermodynamics and are frequently used to derive useful thermodynamic relations. The Clapeyron equation is one such relation, and it enables us to determine enthalpy change associated with the phase change, such as the enthalpy of vaporization, which is denoted by HFG, from the knowledge of P, V and T data alone. Now during phase transition processes like melting, vaporization and sublimation, the temperature and pressure remain constant while the entropy and the volume change. If X is the fraction, if initial phase I which has been transformed into final phase F, then the entropy and the volume, specific volume equation can be written in this way. S is equal to 1 minus X into SI, where SI denotes the entropy at initial phase, plus X into SF. Now this SF, S with superscript F denotes the entropy at final phase. Similarly, V is equal to 1 minus X into Vi plus X into Vf. Now for the reversible phase transition, the heat transferred per mole or per kg is the latent heat given by L is equal to T into SF minus SI. Now dg is equal to minus S dt plus Vdp, or you can say S is equal to minus del G upon del T when P is constant, and V is equal to del G upon del P when T is constant. Now during a phase change process, the pressure is the saturation pressure, which depends on the temperature only and is independent of the specific volume. That is, saturation pressure is function of saturation temperature. Therefore, the partial derivative del P upon del T when V is constant can be expressed as a total derivative, that is dP upon dt when V is constant, or you can say simply dP upon dt, which is slope of the saturation curve on a PT diagram at a specified saturation state. This slope dP upon dt is independent of the specific volume, and thus it can be treated as a constant during the integration of equation, that is TdS is equal to CV dt plus T into del P upon del T when V is constant into dV between two saturation states at the same temperature. Now for an isothermal liquid vapor phase change process, for example, the integration yields T into SF minus SI is equal to T into dP upon dt into Vf minus Vi. So dP upon dt, which is equal to SF minus SI upon Vf minus Vi, is equal to L upon T into Vf minus Vi, shown by the equation 3.8. Now the Clausius-Clapeyron equation can also be derived in another way. For a reversible process at constant temperature and pressure, the Gibbs function remains constant. Therefore, for the phase change at given temperature and pressure, Gi is equal to Gf. Now for the phase change at T plus dt and P plus dP, Gi plus dgi is equal to Gf plus dgf. Now subtracting the first equation from the second one, we get dgi is equal to dgf. Now putting the value of Gibbs energy function as given by the property relation, we get minus Si dt plus Vi dP is equal to minus Sf dt plus Vf dP. So dP upon dt is equal to Sf minus Si upon Vf minus Vi, which is equal to L upon T into Vf minus Vi. Now for fusion, dP upon dt is equal to latent heat of fusion upon T into V double prime minus single prime, where latent heat of fusion is given by LFU. The first prime indicates the saturated solid state and the second prime, that is double prime, indicates the saturated liquid state. The slope of the fusion curve is determined by V double prime minus V single prime, and latent heat of fusion and T are positive. If the substance expands on melting, that is V double prime is greater than V single prime, the slope is however positive. This is the usual case. Water, however, contracts on melting and has the fusion curve with negative slope. Now for vaporization, dP upon dt is equal to latent heat of vaporization upon T into V triple prime minus double prime. Now here latent heat of vaporization is indicated by L vap. The third prime, or you can say triple prime, indicates the saturated vapor state. So this was all for the thermodynamical relations. Thank you.